All right. So my name is Erik Cabetas, and this talk is going to be an overview of interpreted language vulnerabilities. So let's get right into it. So we're going to be talking at a fairly high level. I know this isn't like super reverse engineering conference, so I want to bring it up a little bit, but we're not going to be looking at code or dropping any 0 days or anything like that. Well, maybe one. So the talk is just going to be about interpreted language vulnerabilities and just to try and present more awareness about them. There's been a little bit of research done on this general topic. Dom Brzezinski and Justin Ferguson have done very technical presentations on their findings and audits that happened at Black Hat in Japan and PH Neutral. So let's start out with what exactly is an interpreted language. So whenever you have a high-level source code language and then at some point you want to execute it, whatever that may be, that language, you're going to have code that goes through a language-specific just-in-time compiler, or a JIT compiler, JIT. The JIT compiler will, at runtime, turn your high-level language into bytecode, and then the bytecode gets interpreted in a virtual machine or a dynamic translation engine. These are all synonymous. And across these things, there's going to be optimization steps, and just like a standard compiler, you're going to have abstract syntax trees as intermediaries and things of that nature. And then finally, the VM references any external libraries and gets additional functionality from outside libraries if necessary, and then it executes the native code that it output. So that is basically what the modern interpreted language is. So the classic interpreted language is things like a batch script or a shell script, where line by line, it just interprets the line at hand and doesn't consider code as a whole and has no virtual machine or anything like that. It just executes line by line. So this is the modern interpreted language, so to speak. Picture of said process. Source code comes in. We have a lexical analyzer or a parser. Turns it into, well, also syntactic and semantic analyzers. So that turns it into some sort of intermediary representation, outputs the bytecode, goes through the interpreter, pulls in the functionality from the external libraries, and then you get your final execution results. So when we're talking about interpreted languages, this is the picture that I want you guys to think. And if you've done any threat assessments or just general software security architecture reviews, when you look at this, you should be thinking, okay, there's points here where there's translations, and there's points in the process where different things get translated, being redundant here. At each one of those points, that's where you have an opportunity for vulnerability, right? So your source code might be in a form where the lexical analyzer will choke, or it might get through the lexical analyzer and the syntax analyzer will choke. So depending on what your code looks like, etc., you might have a vulnerability at any one of these components. So things we're not talking about, traditional pre-compiled languages, your C, C++, Fortran, PCL. Everyone still codes in PCL, right? So we're left with these kinds of languages. So these are your modern interpreted languages: Ruby, Perl, Python, PHP, SQL and its variants, as well as JavaScript and everybody's forgotten little cousin VBScript, as well as things that you might not think about, like regular expressions. So, and SQL often people don't think about as an interpreted language, but that's exactly what it is as well. So these are not trivial programs, obviously. These are entire language interpreters. So if you do some shell foo and count up how much C code is in each of these guys, you see there's a tremendous amount of C code. So the chances that every single one of those lines of code is right, zero, absolute zero. So let's talk about some of the bugs we've found in, when I say we found, I mean that have been found in the industry in the past 2 years or so. So not really talking about much of the stuff I've specifically done here, but just a general overview of everything's found. So the first thing I'll talk about is PCRE. Anyone? PCRE? I see head shaking. What does it mean? Perl compatible regular expressions. I expect you guys to say something, because last talk they kept talking to you. Nobody said anything. Yes, Perl compatible regular expressions. So PCRE.org puts out a PCRE library that is used by a whole bunch of projects like Apache, glibc, PHP, etc. Even Nmap, if you knew had regular expression support. I didn't know that. The two most widely publicized vulnerabilities in PCRE were 2005 and 2008. Basically, it came down to there was an integer overflow in the quantifiers, and you could do something like this, tack it in there, and it would generate a heap buffer that was too small and copy too much data to it. So standard heap overflow as a result of an integer overflow in PCRE. So when we think of that whole picture of where this might happen, so let's go back to that actually. So this is actually a bug where, you know, it made it perfectly through the syntactical analyzer and the semantic analyzer, but somewhere after the intermediate language code was generated, the interpreter itself had a vulnerability. And we're going to see a lot of things like that, as well as vulnerabilities in the other parts of interpreter. PCRE itself has a fairly bad history of vulnerability, so it does not get any better for these guys. I think we see a repeating pattern here that if you're using PCRE, expect more vulnerabilities. And notice, compare that to the last slide, the two publicized advisories versus when I opened up the change logs and actually went through the source code and started comparing the fixes checked in with public advisories. So there's some stuff that didn't really get talked about in the public. That happens a lot all over. Open source, closed source, doesn't matter. People fix security bugs, never talk about it. But PCRE is your one common framework for Perl-compatible regular expression parsing. Most people just use PCRE as distributed from PCRE.org. Some projects choose to fork off their own version of PCRE. And then what happens there is you get stuck in the, I need to take upstream patches and continue to patch my security vulnerabilities. But if any of you guys are involved in SDLCs, yes, everyone should be or somehow, you'll find that nobody remembers to do that. It is the last thing that people remember to do. Okay, we incorporated some open source project into our mainline development branch. Great, wonderful, we get all that functionality. Forget about updating security patches and usually forget about updating it, period. It's just gonna get in there, it works, leave it. So this happened with, so yeah, there will obviously be more bugs. So this is the prognostication point. I'm going to predict that there will be more bugs. I don't know. When you fork an open source library and then you don't take the upstream patches, stuff like this happens. So WebKit is the underlying framework for the Safari browser as well as the Google's new browser Chrome. And Safari had a vulnerability in WebKit where their PCRE engine that they forked last year and stopped doing the upstream patching, November of 2007, that's when that started. They had a vulnerability, and Charlie Miller, the Mac ninja, figured out that he could use the same vulnerability that was in the PCRE library here in WebKit, and he won the CanSec West Pwn to Own contest with this bug. So that's PCRE stuff, but there's other languages like Ruby. So Ruby, I think it was July of this year, started getting hammered with a bunch of advisories. You saw that all the CVE numbers just came out. Now these I have up here are only the ones in the language itself. There were another 2 or 3 CVEs that were in components of Ruby, such as the WebBrick web server that comes with it. And those were great vulnerabilities. You could do directory traversal and stuff like that on anyone running a Ruby web server. But these in particular were for the internal functions in the Ruby virtual machine. So all of these, the first one has to do with appending to buffers, strings, manipulation, things like that. The second, fourth, and fifth are all array manipulation, storing into arrays, splicing arrays, things like that. And the third one is formatting of strings. So these are all internal operations of the virtual machine that Ruby has. I think it's called MRI or MIR. I forget what it's called. Anyone? Something. So these are a lot of bugs. It looks like this guy, Drew Yao from Apple, went through and just religiously looked at every internal data type and said, let's find the bugs in here. What if I change this? What if I do that? I get an integer overflow over here, and I get some exploitable stuff. The two highlighted in red, in my opinion, are the ones that are most likely to be remotely exploited. So when we start talking about these bugs, we start wondering, okay, if I have a Ruby on Rails app, how likely am I to get exploited by this? Well, is it your proprietary app or is it an open source app? Proprietary app, zero to little, very, very little chance that somebody's going to be able to blindly exploit you with these types of vulnerabilities. Because you need to know exactly how the source code is laid out. And you need the source code laid out in a very specific manner to exercise some of these bugs, and in an even more specific manner to get code execution on these bugs. So the first two in red are the ones that are a little more generic. The last three, you have to have a very specific code layout to get code exec. So not very likely to be exploited in the wild. But something I did find when I was exploring these is when you have in your mind the code pattern that you're looking for to write exploits for these. So, okay, I need a string appended in a loop to another string, and both those strings have to come from user input. So I want to go out and find all the open source applications that have that paradigm in them, that little thing. What would you guys use? If you're trying to find in all of the open source applications a particular code construct. Something. Grep the internet. How do you grep the internet? Google/code search is your grep for the internet. It's great, supports full regular expressions, PCRE vulnerabilities. And it really helps finding a lot of vulnerabilities. Whenever I find a new bug class, I just drop it into Google code search, and there's a couple thousand open source applications that are vulnerable to it. So with all the work that Drew did, two things I have to say on that. One, obviously there will be more bugs. This is not done with. Drew is good. I doubt he's the best code auditor in the world. Dowd has not even touched this yet. And the next thing is that if you take a look at the Matasano blog, the thread talking about these vulnerabilities, there's an entry from a guy named Dom and a guy named JF, who I referenced at the beginning of this talk. Dom and JF, so Dom states, well, these issues are not new and have been known since 2005, and then he drops a link to his presentation. Fixing the macros is not the right approach, blah, blah, blah. Mats knew it. Mats is the guy that he originally wrote Ruby. Mats knew it, but he did not choose to fix the issues in the 1.8 code. Now it's 2008, and Yao had to rediscover the problems to make something happen. So how many of you guys knew that these things existed since 2005? That guy yawning in the back. Nobody else knew. If you saw Dom's talk, or if you were a black hat paying attention to the security industry, you knew about these vulnerabilities. You knew how to find the code constructs for the vulnerable stuff, and you had a 0-day for 3 years. That's how our industry works. Lovely, huh? And then Justin, his comment right after Dom's is, awesome, just wait until I go public with my JavaScript stuff. So sounds like he's working on some JavaScript language vulnerabilities. And I just emailed him, and he's actually going to be presenting that later this year. So next language to pick on, Python. Earlier this year, around the same time as the Ruby vulnerabilities, it was the summer of interpreted language bugs. So we had Dave, I can't pronounce that, anyone? Rimal? So Dave of Apple Product Security. So you're seeing a common theme here. Apple Product Security is finding all these really cool interpreted language bugs. I think that's nice for the open source world, that these guys allow their security engineers to spend some time auditing these types of products, open source that is. So Dave found a whole bunch of native types, string objects, Unicode objects, etc., that had integer overflows in them, and you could exercise some of these from web applications and things of that nature to get code execution. Justin Ferguson, who I just mentioned a couple times, he found, and this is a really bad one in my opinion, overflows in the Unicode string processing that only affects 32-bit systems. That affects a lot of systems. So the requirements here for you to be vulnerable is that your app accepts Unicode, okay, that's by default, and that you run on a 32-bit platform. That's a lot of freaking people. And he also found some stuff in internal buffer management like Owasp5019 sprintf. And then Google security team, shout outs to those guys. Apple and Google allow their security engineers to find lots of bugs in open source applications and get them fixed. That's pretty cool stuff. So I just mentioned there are some ways to get code paths to execute arbitrary code in these. It's very, very difficult, but there are some ways to do it. And this is presuming that you're not setting up the application yourself, right? So you're trying to find a vulnerable code construct in an existing open source application and then trying to own those applications. It's hard, very, very hard to do that. What would be a lot easier is if you controlled the code construct and you just like ran your own code because you knew exactly how to set up the source code to get your code to execute, to overflow the buffers in the perfect way. So, I mean, but how are you going to remotely exploit that? Like, someone would have to give you a Python shell or some sort of open Python interpreter where you could just put code and run it, right? Like, that doesn't exist anywhere on the internet except for here, Google. So Google has this thing called App Engine, and one of the applications on App Engine is called Shell. So it just lets you put Python code in and run it. Now, it has a very, very tight sandbox. They did a lot of good jobs tightening it down, and Guido, the guy that first wrote Python, he works at Google, so he tightened down the Python sandbox really, really well. But if you see this stuff, these are the sandbox code that he tightened down and left in the source root. So there's all the PYC files of his tightened down internal Google sandbox. So this is actually a design flaw in their particular sandbox. It's not a general Python flaw, but it's a cool way of thinking about how could you exploit a interpreted language bug, right? So this applies to hosting companies. So hosting companies that run PHP with zero-shin and safe mode enabled and all these crazy sandbox lockdowns. What if PHP itself had bugs? That's not a very big stretch. So that's something to think about. Now that, you know, we're not just talking about like server exploiting through a web application or something like that. We're talking about exploiting maybe through a hosting provider and things like that. And of course, you know, there have been bugs found in Python. There will be more. So next to pick on is PHP. I know, really easy. Everyone picks on PHP. It is the bastard child of the security industry. Coding PHP, I actually used to love it. It was my first web application language. I started PHP in maybe 2000. And it's a very basic language. And that makes it very easy to audit. It's also my favorite language to audit. So you can find bugs in it really easy as far as in the PHP code itself, so at the application level. But PHP is basically a wrapper around C. It's a people will kill me for that, I know, sorry. Anyone on the PHP core dev team here? Okay, sweet. But PHP is basically a wraparound C, and C, as we know, gives you a big gun and doesn't really give you an instruction manual. So a guy named Stefan Esser, who used to be one of the core devs of PHP, but because the PHP core security team wouldn't fix any of the bugs he found, he quit the PHP core security team, and then he decided to release all the bugs he found summer of 2007 as the month or life of PHP bugs. Still ongoing, of course. So the total amount of bugs found during the month of PHP bugs is 41, and you'll see some other stats there. But the stat that I want to bring everyone's attention to is the bottom one. So number of vulns not fixed, 5. So why would they not fix the vulns? Well, first off, we can understand why Stefan Esser left, right? He finds all these bugs, and they're like, we're not going to fix them. So why would he stick around and volunteer his time to find all these amazing, amazing vulnerabilities and not get them fixed? So I just read around. I read some blogs. I read some change logs. And it sounds like what happened here was these particular vulnerabilities would have to change the entire architecture of PHP if they were fixed. These were bugs in the core virtual machines of PHP. Now, if you change the architecture of the virtual machines of PHP, what breaks? Anyone? No, well, okay. The apps themselves would work, right? Because you're changing the core architecture, but in general, you get the same paradigm, source code in, execution out, right? So the apps would work. But if you change the architecture of PHP, third-party stuff breaks. And who makes PHP? Zend, a third-party PHP provider, right? So when Stefan's like, fix the architecture, and they're like, no, because our proprietary software depends on that architecture being exactly like that and never being fixed. That's how that works. So that's what I read on blogs. Blogs are true. All right, so where were the bugs found during the month of PHP bugs? So 4 of them were found in extension libraries. So PHP has its core set of 1 billion functions, and then they have an extension set of 20 billion functions. So 4 of them were found in the extension libraries. When you compile them, there's compile options to include the extensions or not. But the 4 that were found were extensions that are commonly found in the default installation of PHP. Another 15 were found in the internal virtual machine. So like the Ruby bugs that I spoke about, these are all the intrinsic data types that are the basis of how the virtual machine operates and how objects are created in that language. Another 22 were available by default native functions. So these are, I said, there's that core huge group of functions in PHP. There were 22 bugs found in those. Now, when I say bugs, I'm usually talking about a buffer overflow, or there might be some reference counter integer overflow that it results in some crazy function pointer being overwritten. Stefan Esser, if you ever read his advisories, like, they're out of this world. That guy is definitely top 10 bug hunter in the world. So what are things that we're not seeing? If you think back to the picture I showed at the beginning, some areas that we're not seeing. So we're seeing the extensions. Remember, off to the left, there's the extensions, right as the virtual machine is executing. We're seeing some native functionality that gets used within the virtual machine and the virtual machine itself. But we're not seeing any of those other areas that I showed. We're not seeing any bugs in language parsers. We're not seeing any bugs in the virtual machine bytecode interpreter. So since Stefan Esser is one of the top 10 bug hunters in the world, in my opinion, and since he found 41 bugs in PHP, so are we secure? Are there more bugs to be found? No, there's no bugs. There's no bugs. PHP is secure. Continue. All right, so JavaScript. JavaScript's been done to death in the last 2 years. Everyone has JavaScript fuzzers. Everyone's mom has JavaScript fuzzers. Some of the big ones written by HD, Avi, and El Kamtouf. Can't ever pronounce his last name, so I just call him by his handle. And they did a lot of fuzzing the DOM, or domain object model, functions within JavaScript. But I show you guys that picture because I really want you guys to think, where in the whole concept of an interpreted language could there exist vulnerabilities? So all of these JavaScript DOM function fuzzers, these are trying to fuzz functionality built into the virtual machine and the extension libraries, right? They're all targeting that. There's a heck of a lot of bugs in there. That's why they're targeting it. For instance, Jesse Ruderman from Mozilla, him and Window Schneider did a talk at Black Hat 2007, and at the end of that talk, they released a tool called JS Fuzz Fun. Now that tool, he wrote in like a couple weeks, and it found 280 bugs in Mozilla. Of those 280, 24 were remotely exploitable. So a couple weeks worth of effort, 24 remote exploits. I think that's a pretty good return on his security investment. Now the question is this, can JS Fuzz Fun be used on other browsers? So by default, no. It has a lot of very Mozilla-specific things in there. But if you spend a couple days and modify it to work with IE or to work with Opera, I bet you will find bugs. Nobody's done it that I know of. So this is kind of like, I'm trying to challenge you guys as well as predict the future. They kind of go hand in hand. So another thing to think about is besides browsers, so now we're in the browser space, obviously. I kind of jumped over from remote execution on server side to client side stuff, right, in browsers. So what else executes JavaScript? Other client type of things? Anyone? Anything else that anyone can think of? Shout it out, shout out. Email? So email, usually, maybe 10 years ago, yes. But all of the email clients right now are very locked down, and they hardly execute any JavaScript whatsoever, if they do at all. So it used to be a vector a little while ago. Anyone else? Sorry. Yelp. Microsoft scripting engine. Interesting one. So that would be like Windows scripting hosts and things like that. Yes, that is absolutely true. Would be very hard to exploit, though. Like, there's not a very easy attack vector, because if you're executing Microsoft scripting engine code, you're owned already. So unless like I give you some code and say execute it, and I use a JavaScript bug in the interpreter to own you, but why do that? PDF, nice. There will be more bugs. Adobe Acrobat supports PDF, and right now there's lots of zero-day bugs going around with JavaScript and PDFs. Why they have JavaScript and PDF, God, I don't know. But it exists, and there's lots and lots of bugs out there to be found. You can take your JS Fuzz Fun or any other fuzzer, and if you know how PDFs work, you can just translate it over and start finding bugs in PDFs. Start sending them to your friends. Good input, thanks guys. So
hey,
kind of,
Eric?
yeah.
What about on the server side for like something like Rhino or Bean scripting frameworks out of Apache?
Yes. No, you're absolutely right. Anything that supports stuff like that will, any interpreted language will have these vulnerabilities. I didn't explore those, but yes, you're absolutely right. You could use that through a vector. Let me get the time here. All right. So, oh wait, let's go back to JavaScript. Bastard little cousin of JavaScript. Something that nobody ever thinks about anymore, and is my favorite way to get past cross-site scripting filters. VBScript, right. So, I mean, has anyone found a bug in VBScript ever? No. Are there bugs? Yes. So start figuring out your VBScript BNF and write your fuzzers, because you're going to find exploits there. Okay, so now SQL, something that people don't really think about as an interpreted language, but at its core, it is, right? So here's the typical bugs found in SQL. When you're doing SQL injection, stuff like that, you've got your SQL manipulation. Let's say you append a union into a query. And then you've got your code injection. That's like if you're appending multiple statements and your backend database provider supports it, like Sybase or MS SQL Server. And then you've got so all this stuff is from a guy named Rahil Ahmad. He wrote an article about it, and I just wanted to take it because of the last part here. So function call injection, that's like if you're trying to execute XP command shell or some other extended procedure or stored procedure, things like that. And then number 4, he puts as buffer overflow. Buffer overflow is caused by using function call injection. For most of the commercial and open source databases, patches are available. The type of attack is possible when the server is unpatched. So if you're in security, you know that these types of attacks are also possible when the server is fully patched. What he means, I think he's got the right idea here. He just didn't generalize it enough, and it's just probably because he's a developer and doesn't understand some of the attacks possible. So not only can you exploit buffer overflows through function calls in SQL, but you can exploit any type of memory corruption bug or design flaws. And if you followed the work of Alexander Kornbus and David Litchfield and Cesar Cerudo, those 3 guys alone probably have, I don't know, what, 30, 40 local root exploits for Oracle just those 3 guys. And if you think they're the only 3 guys in the world looking for bugs in functions in SQL servers, you're wrong. So let's say you have some function, xp underscore do something, and it takes in an argument and an integer for how long it should run or something. You might be able to do multi-threaded stuff, anything of that nature. So what I'm getting at here is, like what happened in JavaScript, you might be able to run fuzzers in this. But why would you try and find a vulnerability in the SQL interpreter? If you have SQL access, like, isn't that what you want? Don't you want the data in the database? So my whole thought process on all of this in this talk started about 3 months ago. I was writing an exploit for semantics reporting server. So it was a remote exploit. You can execute arbitrary PHP code, and it's just a stupid vulnerability where they just take unsanitized user input and just execute it. So there's your 0 day. But it's a useless bug. That's why I'm giving it to you guys. The way that semantic reporting server works out of the box, IIS6 is totally locked down with strict permissions. PHP is installed totally locked down with strict permissions. And it connects to a SQL Server database that's totally locked down with strict permissions. So you've got like 3 really hard layers to deal with there. So my comments up here, all these guys, these were when I was trying to execute commands using system, exec, pass through, include, all those things. I kept getting errors, and I just couldn't get any of my commands working. And that's because of how locked down it was. So I just began thinking, okay, I want to get shell in this box. I want to get my arbitrary code executing. How can I do that? So I just started thinking, okay, what at each one of those layers that I mentioned, the PHP layer, the IIS layer, what can I do here? And then I got to the SQL layer, and I'm like, well, I can't do anything there. It's SQL. But so when you compromise this, obviously you have access to the username and password that the reporting server is using to connect to the SQL server. So you can log right in there and just execute any arbitrary SQL. But it's a reporting server, so I don't really care about the data. I want shell on this box because it's a very powerful box. Every machine in your enterprise connects to it to give information about antivirus stuff. So that's when I started thinking about the stuff that we're talking about, and in particular, these types of bugs in SQL. So where would the bugs live in SQL? And this is very much the same as I was saying with the picture and what I've said with the other languages. Well, first off, there have been vulnerabilities in Microsoft Jet Database Engine, which you guys will know by its other name as Access, Microsoft Access Engine. So there have been buffer overflows found in that. So if you ever had a SQL injection and they were using a MDB file as the backend, you could, back before this was patched, you could actually execute remote code and get onto that machine. But the ways that you would look for bugs in SQL are SQL parser bugs. So you have a semantic level stuff, start throwing in some format strings, large reserved words, column names, table names, things like that. At the syntax level, it expects a certain syntax. If you start giving it things that it really didn't expect, it'll throw reference counters and it'll throw out the parser out of state. And then also what that gentleman mentioned in his article at the function or extended procedure level, and Brett Moore did mention that in his recent paper, Access Through Access. It's like the last page of the entire paper. He's like, oh, by the way, you can also exploit buffer overflows through functions. That was just kind of afterthought. And then just like in Ruby, at the database kernel level, there's problems with primitive data types and things like that. Now, all of these things, nobody's ever published any real bugs in them. So I challenge you guys, write a fuzzer for SQL. You will find a couple dozen, maybe a couple hundred bugs. This guy's gonna do it. So now I talked about it helping me do exploitation to try and get access to a server, right? Well, let's flip that around. So not so much is it a server-side attack, it's also a client-side attack. Now, you're probably saying to yourself, what in the hell is SQL doing on my clients? Well, Firefox ships with SQLite, that version there, as of earlier this year. And the reason it ships with SQLite is because HTML5 requires client-side persistent storage as one of its requirements. And Firefox, as well as WebKit, which means Safari and Chrome, they decided to implement HTML5 a little quicker than everybody else. So they already have a SQL interpreter into the browser. So if you guys want, you can load up a SQL interpreter and just make a database and all in your web browser. Does anyone think that's bad? Like, you're throwing an entire database engine in your web browser? I mean, what is this, Emacs? So somebody laughed. So SQLite, I will say, somebody had a really lucky break. And in June of 2007, somebody filed a bug, and the bug was hilarious. It went like this. I think it's bad that you're using strcpy. I also think it's bad you're using sprnf. Please fix it. And the developer was like, all right, shut up. I changed all of them. That was it. So he just changed all the sprnfs and all the strcopies into sprnfs and strn copies. So by that action alone, just by some guy randomly complaining on the internet, he stopped like dozens of buffer overflows. I was looking back in the old code, and it's horrible. But that's not to say that there are not more bugs. For instance, there are 50 native functions in SQLite. If you start throwing input at those, one will break. And as I mentioned, WebKit ships. Oh, but WebKit ships with its own implementation of SQLite. So it's not the official one from SQLite.org. So WebKit, I've already mentioned before, does its own PCRE. They forked it, and they have their own totally separate SQLite implementation. So you might find a whole different type of bug that you might find in the actual SQLite. So if you make one SQL fuzzer, it will cover every browser that implements HTML5 as well as RDBMSs. So time well spent, in my opinion. I'm too lazy and I got a job, so if you guys want to do that, you will find hundreds of bugs. Okay, so on a last note, I just want to talk about HTML5, because while I was researching this, I read up a lot about it. And the persistent storage I mentioned is section 5.10.2 called database storage of the HTML5 spec. HTML5 is going to be awesome for everyone that works in the insecurity industry. Okay, so what you're doing is you have the most complex software in the world, browsers, and then you're adding on top of that like a whole layer of complex software and integrating them all together and trying to like cover the little channels where data might flow between these two extremely complex layers. It's going to be a bloodbath. So the other browsers, Opera and Internet Explorer, they're working on HTML5 now, but it's a work in progress. So if you read the spec, there's things like allow developers to do this extremely insecure thing by default, and then allow them to opt out of it if they know to opt out of it. And there's lots of stuff like that all over the spec. It's like, do this extremely insecure thing by default, and then allow them to opt out if they know what they're doing. We all know, not good, yes. Very bad thing. So if you guys know anyone that works on HTML5 spec, please tell them to just put a little bit security mindset. And there's actually a guy from Google who's the lead of this spec. So I really hope he gets with his security team and they rewrite this before everyone implements it. Let's see, what else do I got here? That's about it. So I'm Erik Cabetas, and there will be bugs. But before I jump down, one sec. Discussion topics, quick questions? Nothing? Yes? Oh, great question. I didn't mention Perl at all, and that's because I like my sanity, and I like keeping it. I opened up Perl, I looked at it, I cried, and then I left it. Perl is secure because nobody can read it. No, and I'm not talking about the code Perl. I'm talking about the interpreter Perl, right? Perl code can be made very legible, but the interpreter itself is completely unlegible and works. I don't know how. But how about CPAN and Pair? Oh, no. So, yeah, back at the beginning I said extensions are not going to be covered by this, but you're absolutely right. Pair is an extension to PHP, and CPAN is like where you get all your modules for Perl. lots and lots of bugs in those. I suggest if you have access to a static analyzer like Fortify or Ounce or just Rats or something, run it through some, I think WS or whatever the technology is that makes native talk to Perl. Run it on some of the extensions. It's bad. And then Pair, which is the PHP library that comes by default with most PHP installations. It tries to do like a lot of emulation layers. Like it does like stored procedure. Parameterized queries. It does like a parameterized query thing and does not get that right, let's say. And there's lots of bugs out there. So I'll leave you guys find them. All right, thank you.